Right. We are on page 49, page 50 in that area, module 2. And yes, I did bring my, these are not Legos, right? These are Duplos, right? They're like mega Legos. I figured I might as well just bring some in. So if in our metaphor, I reached into the Tupperware container in our basement where what used to be our children's toys and now becoming our grandchildren's toys, reached in there and grabbed a structure that just out of, at random, reached in there, pulled something out, and this is going to be matter, and also it's going to become a molecule for our discussion. So figured might as well just bring a group of Duplos in and start using the metaphor right away. Yesterday we were talking about, we started our conversation about the law of mass conservation, or law of conservation of mass, whichever way you're used to hearing it. I'll accept either one of those. And this basic idea that you have something, and that something through a process becomes some things. Okay? Now that's not the scale, let's say, because what the concept of conservation of mass, or mass conservation, says is that whatever I have in the beginning, whatever mass I have in the beginning, whatever stuff I have in the beginning, after some reaction takes place, I have the same amount of stuff at the end. It doesn't mean that I have the same volume. That same stuff could take up a lot more space. We're going to find out later on that as things go from solid to liquid to gas, the same amount of stuff takes up more space. It takes up more space to have a kilogram of air, let's use water, for example. Well, actually, that's the only anomaly. That's the one that doesn't work. Let's just think about this concept then. It's just as things freeze, as they go to solid, they tend to be small. Maybe let's think between ice and water vapor. A certain amount of water that makes up ice in a cube, in a tray, takes up very little space. But when you evaporate that, when you get it into the air and it's now goes from a solid form to a gaseous form, it takes up more space, more volume. But there's more distance between each piece. If you think about yourselves here in a classroom, if I were to take all these desks and after you got into them, we were to go back to the corner and say, okay, Mr. Van Schuren, don't move. Everybody push back and to the left as close as you can. Let's get as many of you in that corner as possible. And you kind of eliminate the rows and you just flood that corner. And then I said, okay, move your desks back to where they are right now. And say, okay, when was there more of you? You say, what do you mean, when was there more of us? And none of us gained or lost. We didn't gain a student or lose a student. We were just in different formations. At one time we were all packed in a little circle. Another time we were all out here, maybe the clown car from the circus. How many clowns can you get into that Volkswagen? Well, when they're in the Volkswagen, they take up very little space. When all 15 of them come out, and they're standing around with a little bit of space between them because they're more comfortable with a little bit of space, they take up more space, but there's not more or less of them. They're just in a different formation, in a different form. Same thing here. We have a certain amount of stuff. We're just going to say stuff for now. A certain amount of stuff at the beginning, and some reaction takes place. And so in our way we write it's like the math formula, okay? We have something, and a reaction takes place, and the result of that reaction produces some things. But however much matter we had here, we have the same amount of matter here. And we measure matter in grams, or that's the base unit, or other forms using the prefixes millis, killis, and so on, of grams. And so what we ended with yesterday is looking at example 2.1 that said that there's 151 grams of matter that makes tin and oxygen. If we look at the problem again, I'll just read it. A chemist watches 151 grams undergo 151 grams undergo change, collects the tin that was formed, and measures it to be 119 grams. how much of the other material must there be? If this becomes this, and the mass of this is 151, and the mass of this is 119, the mass of the other product of reaction has to be whatever mass we can account for. What can't we account for? We started with 151. We can account for 119. The difference there is 32. There are 32 grams unaccounted for. Where must they be? Well, in this case, they say there are two products of reaction, so they must all be within this second product of reaction, whatever it is. If we said that there were additional products of reaction, if there were not just one, but let's say that we speculated that there were two, what could we say? Well, these two together must be 32 grams. Why? Well, because we had 151, and we've got to account for every gram. And we can't account for 119. What can't we account for? 32. Where must the 32 be? At other yet to be determined products of the reaction. Because the sum of the mass of the products has to equal the mass of the reactants. The amount of stuff we have on this side of the arrow has to equal the amount of stuff we have on that side of the arrow. And that's how we use the law of mass conservation. I don't believe we did on your own 2-1 together, right? Let's go ahead and take a look at that and use this idea. I'm just going to leave this on the board because I think we're just going to deal with basic decomposition reactions at first. The problem here says a compound is decomposed, and this is what decomposition is, right? Taking something and breaking it down into pieces, taking the molecule. If I'm going to decompose this molecule, I start by, okay, it's decomposing, because decomposing in chemistry means taking it apart. So this much has been decomposed, right? I just keep breaking it down. Decomposition continues. Hey, look at me, I'm decomposing, right? You're taking it all apart. I've broken it all down into pieces. Well, guess what? Do I have more or less Duplos now than I had when I started? Same. Same. Okay? Now I know that we're going to have falling Duplos throughout the remainder of this course, so we're just going to have to deal with it, okay? I'll try to get some structure here, because chemistry is mostly about order. There we go. So some semblance of order. On your own 2-1 says a compound is decomposed into its constituent elements of carbon, nitrogen, and oxygen. We talked about this, but we didn't do it on them. So it's how many parts does it break into? It breaks into three different things. Those three different things are carbon, nitrogen, and hydrogen. Carbon, nitrogen, and hydrogen. Okay. Those will make more sense to you as we go start talking about homonuclear diatomics. But carbon, nitrogen, and hydrogen. If in the decomposition there are 12 grams of carbon, 14 grams of nitrogen, and 3 grams of hydrogen, what was the mass of the compound before it was decomposed? So this is how you take the word problem and write it as a chemistry problem. We have something. This is from the last problem. Let me erase that. We have a certain mass of something, and that mass decomposes and produces these three elements with these respective masses. What must the mass of the original have been? How much did we decompose to produce 12 grams and 14 grams and 3 grams? Right. It would just be the sum, right? We would sum all of those up. We would add them all together. So that comes out to be 12, 14, and 3, 0, 9, 29 grams. The sum of the masses of the products has to equal the sum of the masses of the reactants. In this case, there's only one. This must have been 29 grams. Because I can't make 29 grams and account for everything unless I start with 29 grams. Okay? This symbol here, symbol for addition. Sorry, I kind of introduced that. It's beyond the scope of probably what you know, unless you use Excel. But if not, sorry about that. It just basically, this is equal to this plus this plus this. Now, in this breakdown, let's say there's 3 different things. For now, I'm just going to use one of each. It says that we produce something that has carbons, nitrogens, and hydrogens. As a matter of fact, it says carbons, 2 H2s and N2s. So let me go ahead and show something like that. Can you see on this little Duplo structure that I have one red brick? The red brick's kind of big. It might be out of proportion. Let me go ahead and change it to this. How's this? We've got one red brick. They're not all the same size, right? But one red, we'll let that represent the carbon. And we've got 2 nitrogens and 2 hydrogens. Those would be kind of like the blues and the yellows. So this structure here, the way I've drawn it on the board at least, is calling for those 3 different elements. Now, we come up with this idea of an element of carbon, hydrogen, and nitrogen. Where's the idea of element come from? We talked about decomposition. Said the early chemists said, you know what, I know that when I have something, I can take the something and I can break it down. I can decompose it into all of its pieces. And as I take that something, we'll call that a molecule, and we break it apart, I'm going to get to a place eventually where I have something that I can't break down anymore. I can break it down to the individual blocks, but I can't reduce the blocks anymore. We'll call those atoms. The atoms is that piece that cannot be reduced anymore, and the atom that's irreducible. They're not all identical. Hey, I've got something else that reduces down. I can't reduce it down anymore, but guess what? It doesn't look exactly like this one. It's not exactly the same, but I can't reduce this one down anymore either. Oh, and guess what? Over here, I have another type that I've reduced down. I can't reduce it down anymore, but it's not the same as any of these. And this is where we get to the idea of an element. You'll see the definition there on page 50, that an element is any substance that cannot be broken down into simpler components. I mean, if I had these 3 things together and they formed a molecule, okay, say, can I reduce this? Yes, I can. It's not an element. This must be a molecule because I can take it apart. I've decomposed this from this. Now I've decomposed the whole molecule into 3 pieces. But I'm going to get to a point eventually where I just can't break it down anymore. And that is my element. Now we represent elements on this beauty over here, which you are all going to become very familiar with, called the periodic table of elements. The periodic table of elements is structured in a way that you'll come to appreciate over time, that there are characteristics of every element that by how they're placed on this chart, you can gain some insight on how you expect it to behave. There are certain characteristics of the elements by how they're in particular columns and how they're in particular rows, that there's actually a whole lot of information on this table that you may not be able to access quite yet. You look at it, you don't quite see it, but there's a beauty, there's almost like a poetry to this table that you'll come to make sense later on. Right now we're going to just start introducing you to the periodic table of elements. I'm going to try to follow the outline in the book. It'll keep me on track a little bit more before I start just looking at this beautiful piece of work, piece of art on the wall there. Now, actually, if you think of a table like this, you might start to think, hey, if things are grouped together on the table, and I'm just going to believe Mr. Baker when he says this, that they're grouped on this table in a particular way because those things which are close to each other behave more similarly than those things which are far apart. And that is the case. But one of the things also about the table that you need to understand is the table itself, represented flat, is not the best representation of this information. In much the same way as we have this globe, I can represent the information that's on this globe in many different forms. And we're used to two basic forms. One basic form is the globe itself, as a sphere. And we believe, the theory is that the world is round, right? And so we look at this and say, hey, this model of the information most closely approximates what we believe the reality to be. There's another way that we're used to seeing this information as well. And how's that? Same information, but it's shown in a different way. What is that way? Not on a sphere, but rather how? A map. How does the presentation on a map relate to this presentation on the sphere of the globe? Right? It's flat. And in order to make it flat, if you've ever seen a map, they have to do one of two things. They either need to cut it so that what you actually have laying out in front of you is this kind of curvy-looking shape with gaps. Because you can't take something round and squash it flat and keep everything in proportion. Right? I mean, if I were to take that globe and cut it in half, I would still have two hemispheres, two partial circles. And I could take that and say, it's good enough, I'm just going to squish it down. But you squish it down, it doesn't lay flat. We create mountain ranges which really don't exist, right? The best thing we can do is say, okay, one of two things. I can either take that and cut it into small, small segments and approximate it flat, or I can show it to be truly flat, but what I have to do is I've got to stretch out certain areas. And certain areas are going to look much bigger than they really are because I've had to stretch it to fill the rectangular map. So it represents the information, but not in the best way. A better way would be the globe. In the same way, the periodic table of elements is a flat representation that shows relationship between elements. But a better representation would actually be a cylinder. A cylinder. I don't have a blank piece of paper. Let me grab one right here from somebody from another class, from Mr. Parker's classes. If we think about this periodic table of elements as being this piece of paper, but rather than representing it flat, if the truth were that it was actually a sphere, or excuse me, a cylinder like this, it wouldn't be as convenient to hang on the wall, right? You could only see a few elements at a time. You'd have to actually come up and turn it to see the other elements. But what kind of information am I trying to represent here? If I do it as a cylinder, how does sodium relate to neon? On this kind of a flat representation, they look like they're worlds apart, right? Completely different sides of the map. But if I make it into a cylinder, where's neon relative to sodium? If I have one way over here and I have one way over here and they look like they're very, very distant, but then I go, but that's not the way it really is. Here's the way it really is. Rather than being cross-town, they're now next-door neighbors. Okay? So what you need to remember is that these elements over here, though they're portrayed as being very, very, very distant from these elements over here, are really just next-door neighbors. Because the information truly is around and around and around. It's more, also it's not like a circle, it's more of an auger. Because this doesn't line up across, they actually shift. So you go across here, and the next one right here would be here. And goes across, and the next one next door to argon here would be potassium. And across. Again, it'll make more sense as we get exposed to it a little bit more. Now, on the periodic table there are different blocks or boxes, and each one of those boxes represent an element, a structure which cannot be decomposed any farther from its basic form as a building block to make molecules from. Each one of these is an element. 118 boxes. Each one has information about one of the elements. They mention here that 92 of them let me just put it this way. Some of these elements only exist for milliseconds, very, very small fractions of a second, because many of them or not many of them, but the larger ones, most of those are actually synthetic. They're made in the laboratory. They don't naturally occur. Scientists get together and they take two atoms, they smash them together, and they make one new atom. And it exists just for a very brief second, but it did exist, and we acknowledge that by including it. But if you go out into the world and try to collect all the elements outside of the laboratory, you wouldn't be able to do it. The vast majority do exist in that way, but not all of them exist in that way. And they explain in the book how they go about naming them. These ones here, especially with it begin with the U, those are yet to be discovered ones. There's a pattern on the chart that actually, when the scientists that first started putting this thing together, he didn't have all of the elements that we have today, but he knew that they existed because he had a chart that had gaps in it. And he said, you know what, someday somebody's going to discover rubidium. And what's it going to look like? And he was able to say it's going to have this many neutrons, this many protons, this many electrons, it's going to behave in this way. How do you know? Because I have a gap in my chart that needs to be filled by somebody. I just haven't met them yet. One day, it'll be discovered. And sure enough, he was right. Eventually, the chart was completed. So everything that we are aware of that exists can be built from the building blocks represented by these elements up here. Everything that is, that we're aware of, I'm going to caveat that all the time, okay? I'm going to say everything that is, but everything that exists, always here in the background, that we know of, is made of these building blocks. There's nothing that isn't made from something that's depicted up here. Now, every block of information, every block that represents an element has a couple pieces of information in it. If you want to, go ahead and flip to the front of your book, the inside front cover. You're going to need to be very familiar with this chart from the inside front cover. What do we find in every block? Well, this chart that we have on the wall over here has more information than the one in your book. The one in your book is kind of a reduced form. But this is on the, like I said, it's on the inside front cover, so there's no pages between you. You guys don't have it? Some do, some don't. Groovy. All right. Take a peek. Will's on a hunt for it. 52 has a copy as well? Okay. There'll be a copy of this given to you for tests and quizzes and things like that, okay? For the most part, unless you have a particular things you need to memorize that would require that you not have the table of elements, I'll give it to you most of the time. So front cover, or here again on on page 52. So everybody has it on 52. Some of you have it on the front cover. All right, in each one of these blocks, let's go ahead and use sodium. Sodium's very common. So in your book, you'll see a block for sodium. Sodium is a column 1A element. That means look all the way to the left-hand side, then read down to the third block down. You'll see the symbol Na. Two pieces of information in the block for sodium. The number 11, and then below it, 23.0. Okay. Every element that's portrayed on the periodic table, every element has its own block, its own address, and every address has these pieces of information in your book. More on that chart. First, there's a symbol. The symbol that represents that element. I said I'm drawing the block for sodium, right? The abbreviation for sodium is Na. Why Na? You'll notice some of them, like look right above sodium. This is lithium. Does it make sense why lithium is Li? Lithium. Be, it's beryllium. Does that make sense why it's Be? It's beryllium. Okay. Boron, carbon, nitrogen, oxygen, fluoride, neon. They make sense, right? You can see. Next over here, sodium. What? Potassium. Okay. Here's the deal. These abbreviations that represent the elements, they always have at least, or they have two letters. The first one is always capitalized. If it has a second, the second one is always lowercase. Capital CA and capital C lower a mean different things in chemistry. So if you're trying to write calcium, it has to be capital C lowercase a. Part of the reason you need to memorize some of these is that the abbreviation for the elements has one of two sources. It's either abbreviated from the English or from the Latin. Now, if you know Latin, you have a head start. You may have a head start, but you may not have learned these vocabulary words because you're behind. Okay, anyway. Sorry, Will, I looked at you. So, rubidium, strontium, cesium, those make sense. Potassiums, sodiums, and a few other ones that you're going to run into, you can't just reason them out. You can't just write on your paper, oh, potassium, it must be P. It can't be P. Why? Because phosphorus is P. Potassium starts with a P. It also can't be PO. I think we've got a PO in there already, too. Yeah. It can't be PO. We use the Latin. And actually, it's not because the English was full, so we use the Latin. The truth being that it was usually the Latin first, and it later became the English. So some have the English names because they weren't discovered until they were using English as the basic form, or some have the English names because the Latin names may have already used the letters, or there was a development of this process that took place in multiple languages, and the result is the abbreviations for those elements are abbreviated from either the English or the Latin. So you can't assume you know the abbreviation. You've got to memorize many of them, and that'll be one of the exercises you have to do. There's a list of elements that you just simply have to memorize. Now, there's also some other information in this block. Again, give me just a moment. I don't want to get too far ahead because there's lots of information here that we won't need right away. Okay. For now, just here, I'll give you the basics of this information. The first number here is called the atomic number. Okay? The atomic number. Below that is the atomic mass. You may hear the atomic weight be used, but it's not technically accurate. We're not talking weights, we're talking masses. And again, it'll make more sense later on. We've got atomic number and atomic mass. For those of you that already know that information, this atomic number represents the number of protons that are in this element. In one atom of this element, it has 11 protons, and will also then have 11 electrons. The mass number is a weighted average of the number of protons and the number of neutrons. Don't worry about that right now, but I'm just, don't worry about understanding it. I'm just giving it to you right now. The piece here is the abbreviation that every one has its own unique. As a matter of fact, there are no elements that have the same atomic number. Sodium is the only one that has 11. If we look across, we see that magnesium has 12. Aluminum has 13. Silicon has 14. Potassium has 15. They're discrete integer numbers. There is no 14 and a half. There's no 17 and 2/3. They're always specific numbers because they represent the number of protons in the nucleus. And here's the key about the elements. What that element is determined by the number of protons that it has in the nucleus. If I told you, I don't know what this thing is, but it has 11 protons in the nucleus, you would go, well, it's sodium. How do you know? Because sodium is the only thing that has 11 protons in it. But what if it had 12? It wouldn't be sodium, it'd be magnesium. The thing that determines what it is the number of protons in the nucleus. Okay. One of the other major distinctions that you're going to need to be able to make almost immediately by looking at the periodic table is to determine whether or not an element is a metal or a nonmetal. Now, this discussion is actually a long discussion because metals and nonmetals have different characteristics, but for the scope of this course, and I'll say that several times, for the scope of this course, we're going to simplify it. We're going to look over here and say, okay, you'll notice on your table that you have this block on the upper right-hand side that's mostly red, okay? And then right beside that, the area that's mostly green, or it's actually a solid green and solid red block, and it's got that dark black line between them. The squiggly line, more referred to as the black stair-step line. You see what I'm talking about? Right here? Okay. On your periodic table, it's represented here by this red line that stair steps down like this. That line, you need to be familiar with that line because all of those elements which are to the right of that stair step, we're going to refer to those as being the non-metals. And everything to the left of that stair step are metals. Now, metals and non-metals have differing characteristics, like I said, and we're going to grant that when you get close to this stair step, that there's a lot of similarities between aluminum and silicon, and sometimes they have different names. They're transitions, or they're metalloids, they're called. We're not going to get into a lot of depth there. We're just going to say, is it a metal or is it a non-metal? You got to, like I gave you an element. I said, okay, potassium. Potassium, is it a metal or is it a non-metal? Well, you'd have to remember that P is phosphorus, K is potassium. Okay? It's over here. Is it to the left or to the right of the stair-step line? It's to the left of it. Everything to the left of it is a metal. So potassium's a metal. Why? It's to the left of the stair step. What about neon? Metal or non-metal? Non-metal, because it is to the right of the stair step line. That basic distinction between metals and non-metals is very significant. You need to be able to do that. The last paragraph before the blue line on 53 says, elements that appear on the table to the left are classified metals, appear on the right of the jagged line are nonmetals. There are some exceptions to that, and there's a particular exception that you need to be aware of, is that the way that they're presented on the periodic table of elements, hydrogen, because of the way it's constructed, and it'll make more sense later, but because of the way it's constructed, hydrogen is shown to be way over here on the left-hand side, and it would appear to be to the left of the stair step, therefore it would appear to be a metal. But hydrogen is not. Hydrogen is an exception. Hydrogen, when you're saying is hydrogen a metal or a non-metal, for that distinction, hydrogen would be better placed right here. So hydrogen is a non-metal that's depicted on the metal side of the jagged line. So it's the exception. Okay? So now you've got a caveat. Is it a metal or a non-metal? Well, is it hydrogen? No. Okay. Is it to the left or to the right of the stair-step line? But if I gave you hydrogen, is hydrogen a metal or non-metal? If you didn't remember the caveat, you'd say, well, it's to the left of the stair-step line. It's a metal. No, it's the exception. It's over here. But in terms of metal or non-metal, it should be depicted over on that side as a non-metal. Now, part of that is obvious, right? How many of you are familiar with solid hydrogen? You don't think of hydrogen, right? We think of hydrogen, we don't think of hydrogen in terms of metal or non-metal because it's a gas. But here's one of the things you also have to remember about the elements up here, is that every element at some pressure and temperature becomes solid. The reason why we don't think of hydrogen as being a solid or even a liquid, but we think of hydrogen as being a gas, is because of the temperatures and pressures that we live in. We live in a certain range of temperatures and a certain range of pressures. And in that range, hydrogen is always a gas. Okay? But for every element, at some point, think of it like water, at some point, hydrogen actually precipitates and becomes a liquid. And at some point, cool enough, pressure combination, at some point, hydrogen not only becomes a liquid, but it'll actually become a solid. Every element can exist as a solid, a liquid, or a gas. Right? The reason why we think of them as solid, liquid, and gases, as that's the way they usually are, is because that's where we live, in that temperature range and in that pressure range. But again, every element can be, at some point of pressure and temperature, can be a solid, a liquid, and a gas. He says that there's another exception to the rule, and he does actually mention those, the metalloids. The metalloids have some of the properties of metals and some of the properties of nonmetals. But again, for this course, we're not going to get involved. It's just enough for you to know that some of the elements that hang out near and on the jagged line have some properties of both. Some properties of metals and some properties of nonmetals. Embedded on page 53, there are some properties. When I said about they contain the characteristics of metals and nonmetals, he actually lists those out. I was looking for a chart with these, but I didn't see one. He's got them listed in paragraph form. Elements that are called metals, they've got some characteristics. He says that metals, and for now I'll do it like this. Rather than drawing a line, let me kind of embed this idea by drawing a stair step, okay? Metals on the left-hand side and nonmetals on the right-hand side of the jagged line. Metals are what he refers to as malleable. Metals are malleable. So what does it mean if something is malleable? What's malleability? Hopefully, we're all malleable, right? Anybody have an idea? Moldable, right? Malleable means moldable, shapeable. If I take a piece of something and I put it on an anvil and I hit it with a hammer and it changes shape, it's malleable. If I take that same thing, or if I take another thing and I put it on the anvil and I hit it and it shatters, it's not malleable, it's brittle, which is a characteristic of a nonmetal. So if I have something and I can use force and I can shape it, that shaping, we're not going to stand here at the door and look in the class while he comes. Okay, so that shaping, that process of hammering to change its shape means it's malleable. That is a characteristic of a metal. If I take it and I hit it, and rather than shaping, it breaks, it cracks, splinters, and flies all over the place, that's a characteristic of brittleness, and nonmetals have that characteristic. So, if you're told in a paragraph, you have this material, and you hit it with a hammer, and it just explodes and breaks all over, is it a metal or nonmetal? It's a nonmetal. That's why metals like coins, the test for like a gold coin, you ever see those characters where they take a piece of gold and they go, they put it in their mouth and they do that? Yes? No? Okay. That is, I'm seeing if it bends, if it's malleable, because gold is very malleable. I can tell whether a coin is true gold or not by whether or not I can bend it using my teeth. So a check of malleability for the metal. Second thing they mention here is luster. As opposed to lacking luster. Okay? Luster is basically the ability for you to shine it up, to give it a shine. Think of, again, of a gold ring. I can take this ring and I can spend some time buffing it up and it'll shine. You can go out to a jewelry store, buy cleaner and put it in there and clean it up, and after you clean it up, it looks good, but then you buff it up and it gets a nice shine to it. Metals have the ability to, they have luster, which means you can bring out the shine in them. Nonmetals lack luster. Carbon, for example, is a piece of coal. Okay? So if you take a piece of coal and you say, you know what, I'm going to make this piece of coal shine. Or think about it, I'm going to take a piece of charcoal from the fireplace. I'm going to take that piece of charcoal and I'm going to make it shine. You may get a relative shine to it, but you're not going to be able to get the kind of luster, the kind of brilliance, the kind of reflective properties that you're going to get from a metal. It's not worth the effort to do that to it. So the nonmetals lack luster. There's no sense in trying to bring out the shine. Metals you can get those things to shine. They almost seem like they're giving off a light of their own. They don't. They're just reflecting the light, but they can do it very well. And the last thing here for the metals is conductivity. It conducts. So metals are conductors. Nonmetals do not conduct. They act as resistors. They resist. Conductors conduct. Now, there's some resistance in conductors. I understand that. But if you were to make a circuit and you had this length of wire, you can have a non-metal wire. Just we don't understand what the value would be in that, right? Because if I have a wire that's made out of a metal and I hook it up between a battery and a light, and then from the light back to the other end of the battery, I'm going to get a direct current. The light's going to come on. There, we've done something productive. If I have a piece of wire that's made out of a non-metal, I hook it up in the same way, nothing's going to happen. Because no electricity is going to move from the battery to the light. Because nonmetals don't conduct. As a matter of fact, this On Your Own problem here asks that question. On Your Own 2.3 says, if you want to make a wire for an electrical system, and you only have the following elements to work with, which would you choose? Gold, phosphorus. Well, let's just look at them real quick. It's gold. Gold is Au. Not to be confused with Ag, which you'd think that's gold, but that's silver. Au is gold. So we can use gold. What's the other option? It says there in the book. Other options. We've got gold. We have phosphorus. And the third option was, where's Br? Br is over here, 7. Yeah. So I've got those three elements. Those are the three elements I have to work with, and I need to create something that's going to conduct electricity. What would I use? Which of these three elements would I use if I'm trying to conduct electricity? Well, to conduct electricity, does it need to be a metal or a nonmetal? A metal. How do I know if it's a metal or a nonmetal? The jagged line. I'm going to go over here and I'm going to look at this jagged line. And I'm going to remember that this side over here are the metals, and this side are the nonmetals. And I'm trying to conduct, so I need something that's to that side of the jagged line. I'm going to use gold. I'm going to use gold to make it, because if I use those other two elements, it's not going to conduct electricity. My circuit's not going to work. If I were to say, which of those three would I expect to be able to shape and form with a hammer? Again, it's gold. It's a metal. It's malleable. Which of those three could I buff up to bring out a nice shine on it? Gold, because it has luster, because it's a metal. Okay? So if it's to this side, if it's the left side of the jagged line, it's a metal, and these would be the basic characteristics of it. On the right side of the jagged line are nonmetals, and these would be the basic characteristics of it. That's why we're saying there's the metalloids in the middle, the aluminum and the silicon, for example, they're metalloids. Do they conduct or do they not conduct? Well, those are some cases where, yeah, aluminum conducts. Silicon, it occasionally conducts. Okay? It's not hard and fast to the line or to the rule, but for our purposes, we're going to say it's a nonmetal, and therefore it does not conduct. Just that jagged line becomes hard and fast for us for this course. So on your own, 2.2, 3, and 4 all ask questions based upon this table. Is something a metal or nonmetal based upon some of its physical characteristics? Now we kind of take a step back on page 54. We start talking about compounds, because I've already used the idea of a compound as being something that can be decomposed into elements. So while these are elements, these represent elements here, these duplos, they represent elements. As soon as I take two elements and I bring them together, now I have a compound. Elements, a compound. A compound and an element, one compound. A compound and two elements, one compound. Okay? A compound is just that. It's compounded. It's many come together to make one, a compound. So a compound is something that's made up of elements. An element is the most reducible, furthest reducible part of a compound. to kind of, understand both those concepts, you get the whole thing. So you see the definition of 54. Compounds are substances that can be decomposed into elements by a chemical means. So under the definition, discussion of the law of definite proportions. Talk about the work of Joseph Proust in the late 1700s. This idea of definite proportions. Here's what the idea is. Mr. Glenn must be hard at work. Here we go. The law of definite proportions. What Proust and his contemporaries figured out, and look over at page 55 on figure 2.3, this law of definite proportions, is what he found out was that when compounds were being made, let's say, for example, this compound here. I've got a compound here that has a certain amount of red, a certain amount of yellow, and a certain amount of blue, right? In this case, it's one red, one yellow, and one blue, but we could say that each one of these might have different masses. Let's say that this one just happens to have twice as much mass as this one, as the yellow one, and the yellow one has a little bit more mass than the blue one. So each one has a unique mass, but together they form a compound. What he found out was that whenever he was making this compound, according to the mass, at this point they weren't able to look down and say, hey, it's got one of this element and one of this element, and what he figured out in the lab was, hey, whenever I make so much of this compound, I use up so much of each of the different pieces. I left this example up here from before, not to use it, but it'll work. Let's say, hey, I figured out that every time I make 29 grams of this compound, it always uses up 12 grams of one and 14 grams of another and 3 grams of another. It always produces in exactly those proportions. Let's say rather than 29, I had 58 grams. If I made 58 grams of a compound, well, guess what? It's twice as much as my original sample, and it would require 24 grams and 28 grams and 6 grams. Whatever I make, once I figure out what the proportions are, no matter how much I make, I need that same proportion of all of the components. If we had made 5 times as much, we would need exactly 5 times as much of this, and 5 times as much of this, and 5 times as much of this. And the insight that he produced was, hey, whenever I make stuff, I need its elements that make it up. I need them in exactly the same proportion all the time. I never make a certain amount of my compound and have, let's say I made 29 grams, and one time it took 12, 14, and 3, and the next time I made 29 grams, it took 11, 15, and 3. It never happened. It would always work out in these proportions. As a matter of fact, he figured out, hey, if I'm trying to make 29 grams, and I put 12 grams of carbon, 14 grams of nitrogen, and 6 grams of hydrogen into the mix, you know what I'm going to make? I'm going to make 29 grams of this, and I'm going to have 3 grams of this left over. Why? Because I had too much to start with, and they didn't use it. They didn't need it. So this law of definite proportions came about. To make certain compounds, it takes certain elements, and it always takes them in the same proportion to make the compound. And from that idea, and we'll pick up on this tomorrow, is this idea that when I make a compound, the idea, for example, that when I make carbon dioxide, you may remember carbon dioxide, the formula is CO2. Hey, when I make a carbon dioxide molecule, I always need to have 1 carbon and 2 oxygens. If I make CO, it's carbon monoxide, it's not the same thing. If I make CO3, I don't know how to do that, but you know what? When I make CO2, it's always going to be made with the same number of component parts. And Proust and his compatriots, they figured out that, hey, I didn't know necessarily that it was 1 atom and 2 atoms, but what I did figure out is that it was the one set of masses and another set of masses always in that relationship. It's going to take so many grams of this and so many grams of that. Now, I will often refer to formulas in here as recipes. And I want you to understand what I mean when I say a recipe. It's not like when you make a recipe at home, you're making a cake or brownies or something. You pull out grandma's recipe, you look at it, say, this makes an excellent set of brownies, let's say. You're making brownies. This is the recipe I'm going to use. If in a cooking recipe you mess up how much you put in, like it calls for 3 eggs, you put in 4, okay? You're still going to get brownies out, but it's not going to be the same thing. In chemistry, if you're trying to produce something and you put too much of something in, you're either going to produce something different or you're going to produce what you're trying to produce and you're going to have leftovers that are going to sit there. It's basically, if you put an extra egg in the batter, when you were done, you'd have the batter and there would be an egg sitting there waiting to be used. That's how recipes work in chemistry. I'll see you tomorrow.